Yes. Okay, so I thank very much the organizers for inviting me to this conference, and I enjoy also all the questions from this lively audience, so don't hesitate to do it. And I also thank you for the organizers for the warm hospitality. And talking about warmth, I told the students last Thursday that the place where I come from has a temperature that's equal in absolute value to the temperature here. So to illustrate this, I took a selfie just before leaving, actually, and this is what it looks like. Now this has two relations with my talk. I will be talking about phases. So I'm precisely at this place. 3 months ago, I was swimming. So this is a lake. I'm standing on that lake, and I'm not afraid of falling because actually I saw trucks running on it a few days before. And the other thing that's related to my talk is that high-temperature superconductors is basically a misnomer because even at this temperature, this is not superconducting. But I will talk about this. So I remind you that these are layered system of copper-oxygen. We heard many times. And here is basically just the filling of these planes by other atoms would move, in this case, from right to left. So 0 here means half filling. So there are many methods that show D-wave superconductivity in the one-band Hubbard model that looks similar to what is observed here. And this talk is not very well referenced, so but you can look on the web for these lecture notes that I wrote for a school in Jülich in September, where I correct, hopefully, many of the missing references here. So the next talk will discuss this charge density wave by Mathieu Le Tacon, this charge density wave phase that is a subject of much discussion, and for the time being is not being described yet in detail with the dynamical mean field method. So this is a cluster generalization of dynamical mean field theory that Professor Krishnamurthy has contributed developing. That, in my opinion, and I guess Andy also mentions that very often, shows quite convincingly the presence of D-wave superconductivity. So what is plotted is 1 over the D-wave pair susceptibility for clusters of size 4 to 26. And you see that 1 over the pair susceptibility goes to 0. It extrapolates to 0 at some temperature. This is from Mark Jarrell's group. And what gives me confidence that this is representative of superconductivity, of the presence of D-wave superconductivity in the Hubbard model, is that you can use completely different methods based on also non-perturbative, but based on weak coupling ideas that give a very similar TC for the same value of U and the same value of doping. So here we find 0.029, and this other calculation was 0.023. So most of the calculations I will be talking about are done on this cluster that's immersed in a bath of non-interacting electron and that are solved by exact diagonalization. So it looks as if, I don't know why this is showing up. Okay, I knew this would happen. Okay. So even though it looks small, there are millions of states in this problem. So this is, again, the experimental phase diagram of the high-temperature superconductors. I didn't talk about the charge density waves here in this one, but now it goes from, the filling goes from left to right. So the electron dope are on the right, and the hole dope are on the left. So the cellular dynamical mean field theory phase diagram at 0 temperature looks like this. So in blue, the band parameters are taken from band structure calculation. And the antiferromagnetic order parameter in blue here at 0 temperature, you see as this asymmetry that is shown in the phase diagram. It is larger on the electron dope than on the hole dope side. There is some coexistence here that is seen. The width of the phase is larger on the hole than on the electron dope side. But on the hole dope side, we have problems because there's too much coexistence, and in fact, the charge density wave phase is not there. There are many things in this phase diagram. I've talked about that in the school. There's the Mott insulator phase, the antiferromagnetism, superconductivity, pseudo-gap, spectral weight transfers, asymmetric dust. So all this different phenomenology I won't have time to show, but is basically in this one-band Hubbard model with repulsive forces. Hole dope compounds are strongly correlated. So there's evidence from the normal state, which I have discussed at length in the school. So the Mott-Yoffe-Rigel limit is passed, as discussed by Michel Ferrero in his presentation. There's spectral weight transfer, and there is asymmetric density of states, and many other things. In electron dope cuprates, they are less strongly correlated. There's, again, evidence from the normal state. The Mott-Yoffe-Rigel limit is not violated. The pseudo-gap is explained very well with itinerant antiferromagnetic fluctuations, and various theoretical calculations point to this result as well. So before I go discussing more depth what is the physical origin of this superconductivity in this problem, let me go step back and talk about a phase. So a phase have emergent properties. The simplest is the existence of a Fermi surface. So if you start from atoms, they have a discrete spectrum, discrete spectral lines, but you put them together to form a metal and they become shiny, they form a Fermi surface. And it's a property that occurs whether it's electrons in a box or atoms in solids. This is an emergent property. In this case, it's easy to derive, but very often emergent properties are hard to derive from first principle. So what are the, I'm coming back to superconductivity in a minute, but I step back with the antiferromagnetism. So an antiferromagnetic phase breaks symmetries, time reversal, translation by one lattice spacing, and the product of the two is conserved. And if you have antiferromagnetic phase, it necessarily has a spin wave as asymptotically low energy and a single particle gap at least somewhere in the zone. Now there's a difference between weakly correlated and strongly correlated system. Okay, they have the same emergent properties, but as soon as you move from asymptotic lows to zero energy, there are differences. So the magnitude of the ordered moment is different. Landau damping will kill spin waves before we get to J. And in the normal state, they are even more different. In the weakly correlated case, the normal state is metallic. In the strongly correlated case, it's insulating. And the pressure dependence of the T-nail is different. So another way to look at weak and strong correlations for the antiferromagnet is just to draw this phase diagram for a three-dimensional cubic lattice of temperature as a function of U. And then the antiferromagnetism exists all over this region below the red line. So this is a single phase. Whether U is big or large is a single phase. Nevertheless, properties are quite different. I will talk about this line in a minute. If I come from this way, I come from a metal towards the antiferromagnet. And the physics is that of nesting, Stoner antiferromagnetism. On this side, I come from localized moments. And the physics of ordering here is the physics of the Heisenberg model. And if you think of the pressure dependence as modifying the ratio of T over U, then pressure would be moving to the left on this diagram. And you see that the pressure dependence of the nail temperature is quite different depending on if your magnet is weakly or strongly correlated. And this line is the Mott phenomenon. In other words, you want to go from something that looks metallic to something that looks like a local moment. And it's a non-trivial crossover that is best described by dynamical mean field theory. So if you remove the antiferromagnetism and try to describe what happens to this line by a mean field theory all the way to 0 temperature, what you find is a first-order transition that ends at a critical point. And in fact, this critical point is seen in B2O3 and the BEDT organics, but in many cases, it is just not seen. I mean, antiferromagnetism goes above it. But the crossovers are seen. Okay, now to the main point of my talk, which is the difference between weakly and strongly correlated superconductivity. So I mentioned that there's a difference between weakly correlated antiferromagnetism and strongly correlated antiferromagnetism. Is there a similar difference for superconductors? Well, the emergent properties are the same, whether it's weakly or strongly correlated. So, for example, in the case of D-wave superconductor, UR symmetry is broken, but rotation by 90 degrees is broken as well. There's a single particle gap and a point or line node, and that determine the asymptotically low temperature dependence of the specific heat, thermal conductivity, and various other properties, the structure of the goldstone modes. But there are things that are more specific to strongly correlated superconductivity. For example, Tc does not necessarily scale like the order parameter. Superfluid stiffness scales like doping a Mott insulator instead of filling. Superconductivity can be largest close to the metal insulator transition. And what I will mostly discuss in this talk is resilience to nearest neighbor repulsion, which is very different whether you're weakly or strongly correlated. So what is the mechanism for a weakly correlated superconductor? Well, this was found even before, this was suggested even before ITCs were discovered, based on earlier ideas of Kohn and Lottinger, where what is exchanged here is not a phonon, like in ordinary BCS, but it is antiferromagnetic spin fluctuation. Now, if this potential is repulsive, the BCS equation can nevertheless have a solution if if U is large near pi pi, then you can compensate the minus sign by changing the sign of the gap itself. So in this weakly correlated case, you can use other methods than you can use dynamical mean field theory. I will show results, but you can also other methods that give similar results. And so this approach, two-particle subconsistent, satisfies the Merman-Wagner theorem, conservation laws, and Pauli principle. And if you look at the D-wave solutions, the conditions for superconductivity are different from what you would find in simple BCS. So in BCS, all that comes for S-wave is the density of states. But here, actually, nesting or pseudo-nesting of the Fermi surface determines whether you have dx squared minus y squared or dxy, for example, superconductivity. Also, there can be, if you plot Tc as a function of frustration, T prime, that's its diagonal hopping, you see that there's an optimal, there's such a thing as optimal frustration. So in these calculations, they're done with Syed Hassan, who is working here in India. The antiferromagnetic correlation net is of order 10 at the optimal Tc. Okay, now we look at the strongly correlated. What is the mechanism when you have strongly correlated? Well, the first one that was proposed, again, before the high Tc, is just to take the Heisenberg interaction and do an anomalous pairing of the C dagger C, like you do usually in BCS. And you find that now a mean field solution where J has a minus sign in front of it, so it is attractive for D-wave pairing. So it is, the idea is credited by Anderson to Pitiaevsky and Bruckner, where the pair state is orthogonal to the repulsive core of the Coulomb interaction. So, okay, so now high temperature superconductors, the view from dynamical mean field theory. So we do these cluster calculations that I mentioned in the first, one of the first transparencies. And there are many calculations by Andy Melis's group also using DCA, and Mark Jarrell's group, and some collaborators here in India. So the positive aspects of these dynamical mean field calculations among the many positive aspects is that long-range order is not done in any mean field way on the cluster. You just assume symmetry breaking in the bat, and you see if it is self-consistent. What's included is short-range dynamical and spatial correlations. And what is not included is the long wavelength particle-hole and particle-particle fluctuations. Okay. So what is the pairing mechanism at the strong coupling? Well, if we just look at the value of the order parameter, this is a plot of the order parameter as a function of filling. So F filling is here, is 1. And if you are at if you're not in the Mott insulator at F filling, so U is half the bandwidth here, if you don't allow for antiferromagnetism, you see that the order parameter goes up all the way to F filling. If you are in the strongly correlated case, in other words, the system is Mott insulator at F filling, you have this dome shape for the order parameter, and you can check that if you divide the order parameter by J, as U gets larger and the Heisenberg Hamiltonian becomes, or TJ Hamiltonian in this case becomes better, you see that the order parameter scales like J. So the optimal value of for superconductivity is when you're close to the Mott transition. Yes?
So the bath has some broken symmetry.
Yeah.
And it is self-consistently checked with the cluster that you're keeping?
Exactly. I mean, so the cluster does not have any broken symmetry, but in the calculation you solve this cluster where and in the bat you put an anomalous averages, and then in the DMFT clustered DMFT self-consistent solution, you see whether this gap survives or not. So the glue. So this goes back to a question that is asked by Philip Anderson, who says that many theories about electron pairing and cuprates may be on the wrong track. So this was drawn by the editors of Science, where because in his paper he says we have an elephant and a mammoth. So the mammoth presumably is U and the elephant is J. In the refrigerator, why should we care about the mouse, which is the spin waves at low energy? Well, the key is, another way to frame this question is what about retardation? So let's go back to just ordinary electron-phonon interactions in lead. So what is plotted here, taken from this paper, is the imaginary part of the anomalous self-energy, the off-diagonal self-energy, as a function of frequency. And this is absurd. You can extract this from tunneling curves. And you see that these two peaks here are the same as those that you see in the phonon spectrum that's measured by neutron scattering. So if you just shift by the gap, you see that these coincide. And you see replicas of these here that were seen experimentally and that are quite convincing arguments. The other point I want to point out is that this imaginary part can become negative. It's an off-diagonal component, so causality does not restrict it to have a single sign. And so I will come back to the meaning of this negative part in a moment. So here is what we find for the glue now in these cluster dynamical mean field calculation. So I plot again the imaginary part of the self-energy as a function of frequency in units of hopping. Again, there are two bumps, and these are just different dopings. So this is very close to F filling, and you go to the overdope region this way. These are the corresponding curves for the single site spin susceptibility. So as you see, there are two bumps also in this is this chi double prime. And if you just take the maxima here and draw them as these purple dots, you see that they follow each other. The same for this other curve. If you look at experiment for there's experiments by the group of Birgeneau that looked at the size of this low frequency bump here. And what they see is that it goes to 0 at the same time as TC in the overdope side goes to 0, which is consistent with this. And if you look at the shape of the spectrum of this chi double prime measured experimentally, then this is, you see this two-bump structure in this general area. And if you go to the normal state, you see that the low-frequency peak disappears, and this shifts to the right. So the red curves here are in the normal state. So you see that the low-frequency bump has disappeared, and it has shifted to the right. So all these qualitative aspects are there. Okay. Now, what frequencies are important for pairing? What is the effect of retardation? So we will focus again on the anomalous Green's function. And I'm introducing a new concept here, which I call the cumulative order parameter. So I'd like you to remember this, because we will use it over and over again until the end of the talk. So if I take this, the spectral weight for the anomalous Gorkov, the Gorkov function, or the off-diagonal component, and if I integrate this from 0 to infinity, I get the equal time, I get the order parameter, basically. And if you look at this equal time correlator here, and you look as a function of distance, so as a function of L minus M, it will give you the superconducting coherence length. It will decay with this length. So, so what we suggest here is that we should look at this frequency dependence. In other words, we cut off the integral at some frequency omega, and that should tell us what is doing the pairing, what frequencies are important in pairing. That's an unusual way to look at this, but so to understand this, we look at the familiar cases. So this is this cumulative order parameter as a function of frequency, and so that's this upper bound here. And this is for a BCS D-wave superconductor. So it goes up until the cutoff, because in BCS there's always some cutoff, the bifrequency. And then you've reached the asymptotic value. Now this is a calculation for lead, the dashed line. So it is shifted by the gap. And you see the transverse phonon frequency, the longitudinal phonon frequency shifted by the gap. And you see that it overshoots the asymptotic value of the order parameter. It comes down here. So why does it come down? It is this negative part of the anomalous self-energy that I was pointing out earlier that makes this go down. And in fact, if you look at the Eliashberg equations, where this comes from, and you remove this so-called mu star, which takes into account Coulomb repulsion, what you will find is that it is flat. So this going down here is the effect of the Coulomb repulsion. But it occurs at larger frequencies, so it does not kill completely the superconductivity. We know that retardation is important. You don't want the two electrons to be at the same spot at the same time. So you scatter off a phonon, and then another one comes in. Yes, Mathieu?
Just omega is a function of t here?
Yeah, the units are, I should have mentioned, is always hopping, little t. So this is the result of the calculation for the phase diagram I showed you earlier. So if you look at in the overdope system, it looks, it looks a little more like BCS. It goes up, and then it's almost flat immediately. In the underdope region, that's this line, it overshoots more. Before it comes back. So as you get closer to F filling, repulsion has some effect at high frequency. And this is the optimally doped case. So if you look at this scale, it's of order J. Yes?
Is this TPSC?
No.
This is DMFT?
Yes, this is DMFT. So starting from starting from here, everything is CDMFT. So TPSC is not valid in this region. This is all strong coupling. Okay. This is U equals, I should have mentioned, thank you. This is U equals 8. And this is the band structure parameters for YBCO. Okay.
So then I'm coming back to the
Yes?
So you were saying J on this plot?
The J on these plots is basically, if you go halfway to reaching this, I have plots to show this, I didn't put them, but if you go halfway up to the asymptotic value here, and then this is basically J. Except that J weakens as you go to overdope. But the scale is J. It's perhaps half J or twice J, but okay. Now, nearest neighbor repulsion. Well, the Hubbard model is nice, but we know that in real life there will be repulsion. And this is very worrisome because, in fact, it looks like a killer. If you look in the weakly correlated case, there are several papers that show that if V is larger than U squared over the bandwidth, you destroy superconductivity. If you look at this mean field way that I showed about superconductivity, this Varma-Schmidt ring, if V is larger than J, no more superconductivity. Yes? Yeah, the band parameters are for... Yeah. There is a perpendicular hopping, but I look as a single plane. Well, okay, so the sad part is that if you just estimate V from the Coulomb interaction and the dielectric constant, it is much larger than J in the cuprates. So if somebody tells you J is causing the pairing, you have to ask why isn't V destroying it? Or explain to me why screening is so good in this bad metal. Well, in ordinary Eliashberg theory, the effective Coulomb interaction is screened in the sense that it occurs over a very large frequency scale compared to the pairing. So if you sort of fold this down to the Coulomb interaction in the low frequency range, you will see that it is reduced in this way. But there's a log over E Fermi times the Debye frequency or the cutoff frequency. And in high temperature superconductors, these scales are not the same, but they're certainly much more comparable, 5 minutes, yes, than in the ordinary superconductor. Okay, so if we look at weak coupling, this is the order parameter as a function of doping. This is the V equals 0, so no near neighbor repulsion. U equals 4, T equals 1. If I go to V equals 1.5, you see that I got rid completely of superconductivity. Now take U equals 8. U equals 8. Now I can go to V equals 3, and nothing has changed here for the order parameter. It's quite resilient. In fact, if you look at this ratio, 1.5 over 4 or 3 over 8, it's the same ratio. And here it kills superconductivity. Here it does nothing. So if we look at this cumulative order parameter, you see that there in this overdope region where it's more sensitive to V, a little bit like at weak coupling, then V equals 0 is this red curve. And as I go to the black curve with V equals 3 in this overdope region, you see that everything always goes down. Very different in the underdope region. If you go to the underdope region, you see that if I put V, again, the red is V equals 0. Now I put V equals 3, and now it gets larger at small frequency. So why is that? Well, the physics of J, as you know, is the degenerate second-order perturbation theory. So I look at hopping and coming back. The energy denominator is U. J is 4T squared over U. Let me put V. What happens with V? Well, if I have the two electrons here at their original positions, then there are 7 V's that come in. Now, if this goes there, there's an energy cost that is U. But now you have only 6 times V because you have these three V's, and then the extra electron has also V, so it's 6 times. So in fact, V reduces the energy denominator. So J has increased by putting V. So V is not only repulsion. When you have this possibility of having a J, it's also attractive. So we can look at these curves again and see, for example, that at U equals 16, then for V, this is underdope, x equal 0.05. You see that at V equals 0 and V equals 8. So in going from V equals 0 to V equals 8, you change 4t squared over U minus V by roughly a factor of 2. And you see that this goes up by roughly a factor of 2. But yet, at high frequency, V is doing its thing, so it's killing this much more. When V is large, well, this effect of Coulomb repulsion is there. It kills this. And also this range here, J changes by a factor of 2, and this range changes by a factor of 2 in going from there to there. If you look at the density of states, I suppose I'm finished now. If you look at the density of states as a function of frequency, then there are, this is the underdope regime. You have the pseudo gap, and you have this superconducting gap here that is much smaller and does not depend that much on V. In the overdope regime, then it depends more on V, and that's the superconducting gap, and that's the pseudo gap. And what do I want to say here? Yeah, you see this asymmetry between electron and holes here that is very important. Okay, so now I have to skip all of this. I'm just going to perhaps show that the density of states in the superconducting state in the highly underdoped case is very asymmetrical, like the normal state. So the superconducting state remembers the normal state. It's not a simple BCS superconductor. It becomes more electron-hole symmetric at large doping. And this is a result from Andy Melis's group, where rho S as a function of x, again, scales with x at small doping. C-axis, sure, yeah, important. Otherwise, I mean, you could neglect the vertex corrections. Yeah. So quantum methods, quantum cluster methods, so generalizations of dynamical mean field theory, are excellent tool to understand strongly correlated superconductors, including the strange metal, which I didn't have time to show. TC does not necessarily scale like the order parameter. We have results for this, but I haven't shown. Superfluid stiffness scales like doping. Superconductivity can be largest close to the metal insulator transition. And this resilience to near neighbor repulsion is a very important and at strong coupling. And I think also clearly illustrates another way of seeing that J is doing the thing, and that it is not a simple mean field thing. The frequency dependence is extremely important. So retardation plays an important role here as well. So these are collaborators. So I've mentioned, whoops, sorry. So I mentioned, so this work on resilience was mostly David Sénéchal, Alexandre and Vincent Boulian. And the early work on the cluster CDMFT were done with Marcello Civelli, Sarma Cancharla, Massimo, and Gabi. And some of the TPSC work by Hassan and by Bob Sukyung. And these are sponsors, and these are computers, and thank you.
Okay, thank you very much. The questions and discussions.
Since you find that the V is very important, do you also see this charge density wave in your?
Well, that's the next step. I mean, we need to see what the implication for the charge density wave, but then you need to do so-called inhomogeneous CDMFT because it's larger than the cluster. And also anything incommensurate, we will have problems seeing.
Can you explain a little more about how you treat V? I mean, in particular, if you do CDMFT, are you keeping the V just inside the cluster?
Yes. So we keep V inside. That's a very good question. We keep V inside the cluster. And outside the cluster, we keep it in Hartree-Fock. And then we check that this is correct by looking at half filling and seeing that indeed, if we look at the spin fluctuation spectrum, we verify that J is equal to 4t squared over U minus V, and not V over 2 or twice V or something. So even though we did Hartree-Fock for the largest neighbors, still we retain this physics here. So this is what gives me confidence that it's working.
concerning the estimate of the U minus V. So this, if I understand correctly, is something like the effective local U that you would calculate, for example, in an EDMFT treatment, right? And if you have a nearest neighbor V, you would also in principle have a long range tail. You have a next nearest neighbor and next nearest neighbor. So if you do the EDMF calculation, you find that if you truncate that series after the first neighbor, you get indeed U minus V, but this is a very, very rough lower bound if you keep the long range tail. And then things also depend on the one particle band structure and the regime you're in. So you might overestimate the effect of V if you just take U minus V.
Okay. But, okay, I guess, so this is sort of a worst case scenario. It shows that even if V is large, you don't kill superconductivity. And, yeah, but, okay, but I mean, the question then I'm asking you is that we want to know both the low frequency and the high frequency effect. So if you're saying that I'm modifying the U effective at low frequency a lot, how am I modifying the high frequency? I'm modifying it also. And in which direction are we going?
I'm probably biased by the EDMFT treatment, but if you look at U of omega as screened by intersite interactions, you would always go back to the bare interaction at high frequency.
Yes, yes.
But at low frequencies, you will only find U minus V if you just keep nearest neighbor interactions. If you have the long range tail, you will get something bigger, which depends on the regime you're in.
Okay, so you're saying that I'm overestimating the binding effect of G.
Yeah, let me ask a quick question. You said electron-optic plates are weakly correlated.
More weakly correlated, yes.
The parameters are different. For example, U is smaller.
U is smaller, yes.
Yeah.
So, and the electron dope are simpler. I mean, there's only antiferromagnetism and D-wave superconductivity. And the pseudo-gap line you can explain just from antiferromagnetic fluctuations. And there are predictions that the pseudo-gap appears when the antiferromagnetic correlation length becomes of the order of the thermal de Broglie wavelength, and it's observed experimentally. And there are predictions that Z, the dynamical exponent, should be 1, and it's observed experimentally. So, I mean, when antiferromagnetism and superconductivity get together, then all hell breaks loose, and it's very hard to treat. But otherwise, it seems to be, it's relatively simple to explain.
Okay. If there's no more question, let's thank the speaker again.